Hey, this is Chapter 8, Hypothesis Testing for Population Proportions. And we're going to look at sections 8.1 and 8.2 today, the essential ingredients of hypothesis testing and hypothesis testing in 4 steps. All right, number 1, in Chapter 7 we learned that confidence intervals are a type of statistical inference that can be used to estimate parameters based on the results of a sample. The margin of error for these intervals allowed us to quantify how confident we were in these estimates. So we can keep that in mind that we were estimating parameters, coming up with a range of values that were plausible for that parameter. In Chapter 8, we're going to learn how to use hypothesis tests to make a decision about whether it is likely that a population parameter is equal to a hypothesized value. And so it's going to be a little bit different. We're going to have 2 choices to choose from. And those 2 choices are in the null hypothesis and the alternative hypothesis that we'll be learning about shortly. All right, so for some examples, in each of the following cases, a person is interested in making a decision about the value of a population parameter. 1, a researcher is interested in testing whether a new medical treatment is effective at increasing the survival rate for a disease. 2nd one, a pollster is interested in whether the public support for a candidate has decreased after a recent scandal. And the 3rd one, a gambler wants to know whether or not the dice being used at a local casino are fair. Hypothesis testing is another type of statistical inference that will help us choose between 2 claims made about a population parameter. So for instance, that researcher up in number 1 up there is interested in whether the new medical treatment is either effective or not effective. So here's the 2 choices that person's going to be choosing between. All right, the pollster is going to be interested in whether the public support for a candidate has either decreased or stayed the same. So here are the 2 choices that they're going to be interested in choosing between. And the 3rd one, the gambler's going to be wants to choose between whether or not the dice are fair or biased. So and there you've got 2 choices that they're going to be choosing between. So these decisions are going to be made based on a sample statistic. So that's a key word there. So they're going to be collecting a sample and calculating a statistic from that sample. All right, number 3, given that statistics vary from sample to sample, the decisions we make regarding these parameters are uncertain. So how do we make these decisions? How do we know if we've made the right decision? And what's the probability that we make the wrong decision? Hypothesis testing provides a method for making these decisions and allows us to control the probability of making certain types of mistakes, i.e. the chance that we make the wrong decision. There's one general approach to hypothesis tests that we're going to be looking at, and it's a 4-step approach. And we'll be looking at these 4 steps in more detail on the next page. But your first step is to do the hypothesizing. In other words, you're going to write your 2 hypotheses. So I think it was these 2 choices we looked at up here. Your second step, you're going to prepare. And more specifically, you're going to be looking for a method for measuring how often you make mistakes. And you're going to be setting something called the significance level. And again, we'll learn more about that on the following pages. Your third step, you're going to do some calculations. And you're going to be making some comparisons. Okay, so you're going to calculate that test statistic we talked about up above. So this is structured to compare your observed statistic, what you get from your sample, to what you would expect to see if one of those choices were true, one of those hypotheses were true. All right, and number 4, that last step, you want to interpret your results. So you want to summarize what you found. So that step, you're going to be looking at the surprise factor. So if the value of your test statistic, again, what you get from your sample, is so big or so large that it occurs only rarely when an original or null hypothesis is true, then you might come to the conclusion that you would reject that hypothesis. All right, so let's use an example to illustrate the 4 steps in a hypothesis test. So how can we test whether the die we are rolling is fair? So step 1 is where we state our hypotheses. So step 1, state a hypothesis about a population parameter, which is a claim about the world, and an alternative hypothesis. So those 2 choices we're interested in, choosing between. All right, so we start with the null hypothesis, and we use this notation, H with a subscript of 0, it's H naught, or the null hypothesis. And this is your status quo. So it's the prevailing viewpoint about a population parameter and states that the parameter of interest is equal to a specific value. So we're going to be limiting ourselves to an equal sign in this statement. right, so in our example, the six-sided die that I have in my hands is a fair die. This means that the number 6 is just as likely to be rolled as any of the other 5 numbers. In other words, 1/6 of my rolls will result in a 6. So we can express this hypothesis using symbols. And since we're talking about a proportion, we're going to use P. And for now, again, the status quo is that die is fair. So we're going to say that P is 1/6. All right, so in this case, this value is equal to P with a subscript of 0. And that's just a reminder that this is in the null hypothesis. Because we're going to assume the null hypothesis is correct until we gather enough evidence to suggest otherwise. Okay, and one other thing to note in this null hypothesis is that we're always going to be using an equal sign. Okay, our textbook is going to do that as well. Other textbooks or further and more advanced statistics classes may change that, but again, for now, our hypothesis, our null hypothesis more specifically, is always going to be in the form that this proportion is equal to a null hypothesized value. All right, the second bullet, the alternative. So we then state an alternative hypothesis, and we denote that with H and an A for alternative, which is an alternative to the null hypothesis, the change in the population parameter that the researcher hopes is true. So the six-sided die that I have in my hands is not a fair die. The 6 does not appear in the same proportion of times as the other 5 numbers. And we can express this hypothesis using symbols as well. So this is the key word here, that the 6 doesn't appear in the same proportion of time as the other 5 numbers. So we would say that P is not 1/6, or is not equal to 1/6. And you notice that this is that same value that we had in our null hypothesis earlier. All right, so as an example, kind of a counterexample, let's say that they thought that the 6 appeared more times than it should. Then they might say that the alternative hypothesis is that P is greater than 1/6. So we'll just put a note here that that's more 6s than you would expect. And then the other option is that maybe the 6 doesn't come up enough. So we would say that the proportion of 6s is less than 1/6. So that's less or fewer 6s. And those are really your 3 options in this particular chapter. So when you do your alternative hypothesis, you're limited to these 3 choices. You can say that P is not equal to the null hypothesized value, P is greater than the null hypothesized value, or P is less than the null hypothesized value. And the choice between the 3 comes from the statements that are given. So that, draw the arrow up here, this is what told me which of the 3 to choose for our particular example. And keep in mind that the alternative hypothesis is the one that the researcher kind of hopes or wishes to convince to the public is true. And one last comment, if you look more closely at these 2 hypotheses, notice there's no overlap. So there's no common value between the 2. Okay, so these hypotheses must be specified before the sample data are collected. So again, that's a big piece of this. That's why it's step 1. Significance test is designed to assess the strength of evidence against the null hypothesis, and we will assume that the null hypothesis is true until we collect enough evidence to suggest otherwise. So keep in mind all of the following steps, steps 2, 3, and 4, are going to be carried out with the assumption that the null hypothesis is true. And a null hypothesis, or a hypothesis test rather, is similar to how our justice system works. We assume the defendant is innocent, that's your null hypothesis, until there's enough evidence to conclude otherwise. In other words, choose your alternative hypothesis. Okay, and the last comment before we go on to the next page is keep in mind that the null and the alternative hypotheses are not something that technology is going to set up for you. It requires an understanding of the context of the problem. Okay, so step 2, determine how you will use the data to make your decision. Step 2 also involves choosing what's called a significance level, and we're going to learn more about this a little bit later. So this is a little bit unusual. We're going to save that part of step 2 until the end for now. All right, so assuming the die is fair, we know that our samples of rolls would typically result in a 6 around 1/6 of the time, give or take some variability. The question is how much variability? So we can use the central limit theorem, or CLT, to create a sampling distribution for the proportion of 6s in a random sample of 60 rolls of a die if the following conditions are satisfied. And these conditions are the same ones that we observed in the previous chapter. So condition 1, we have to see if the sample is random. So assuming we're rolling the die in a random way, we can say yes. And then the question of independence. So is each observation or roll of the die independent of the others? Again, we'll have to conclude that that's yes. One roll's outcome is not going to affect the others. And as a reminder, remember that condition 1 impacts the center of your sampling distribution. So if that condition hasn't been met, we won't know where the center of the distribution is. All right, condition 2, is the sample size large enough? So we're going to be doing 60 rolls, and we're about to find out why we're doing 60. Is our condition or our test for sample size is the same as before. So we're going to check to see if n times p is greater than or equal to 60, and whether or not n times 1 minus p is greater than or equal to 60. And like before, both of these have to be met. So for this first one, we're doing 60 times 1, 6. Notice that gives us 10. So if we had done any fewer rolls, we wouldn't get to 10 for that condition. And here, 60 times 1 minus 1, 6 is 50. So we can say, yes, this condition has been satisfied. And again, thinking back, if you remember, condition number 2 affected the shape of the distribution. All right, condition 3, we want to check if our population is at least 10 times our sample size. So our population, capital N, population size, should be bigger than 10 times 60, which is 600. And we can say, yes, it's met, because there are more than 600 rolls. In fact, we might even say that there's an infinite number of rolls, or infinitely many rolls of the die that are possible. And condition 3, remember, had to do with the spread. And we can't predict the spread of these distributions if that condition hasn't been met. All right, since our conditions have been met, we can go on to step 3. So step 3 says, since all 3 conditions for the central limit theorem have been met, we can create a model for the sampling distribution for p hat. So remember, we are assuming the die is fair. That's our null hypothesis. And so we have evidence to suggest otherwise. All right, so the sampling distribution for p hat is approximately normal. That first condition was met, so we know the shape. It's going to have a mean equal to the null hypothesized value. So that's our 1, 6. Because again, we're assuming the die is fair, or we're assuming the null hypothesis is true until we get any other evidence to suggest otherwise. So again, keep in mind that comes from your null hypothesis. And then we can also get a measure for the spread. We're going to call that standard error because it's still referring to a sampling distribution. And notice that p with a subscript of 0 is in here, and that's designed to remind us that we're still assuming the null hypothesis is true. So we don't have any evidence to suggest otherwise yet. So we do 1, 6 times 1 minus 1, 6 over 60 is our sample size. And again, what you may want to do is press pause and verify this number. So you get a standard error of about 0.05 or 0.048. All right, so step 3, this is where the observed value of the statistic is going to be compared to the null hypothesized value. So we're going to need to compute a test statistic and a p-value. And we'll see that on the next page. Okay, so we need to complete the sketch of the sampling distribution for the sample proportion of 6s when a fair die is rolled 60 times. So my horizontal axis is sample proportions. So these are all the p-hats that would be possible if I rolled a fair die 60 times. All right, so from the previous page, we know the center of this is going to be at 1, 6. And I'm going to convert that to a decimal just to make things easier for us. That's at 0.17. And then our standard error was about 0.048. So standard error, 0.048. And I'm going to round that to 0.05, and just to make this a little easier on us. So let's see, 1, 2, and 3 standard errors above. So that's going to be 0.22, 0.27, and 0.32. Then I want to go 3 standard errors to the left. So that's 0.12, 0.07, and 0.02. And again, the key here is that we're still assuming the null hypothesis is true. So all these values in your horizontal axes are possible sample results for rolling a die 60 times. They're all the proportion of 6s you might see. All right, one last piece here, the sampling distribution, we can say is normal. And it's centered at 1/6 and has a standard error of 0.048. And I'm going to just keep the more exact value in that notation. All right, next step. You're going to roll your die 60 times and calculate the proportion of rolls that result in a 6. So note, if you're listening to this at home or doing this activity at home, then you can use the dice roller at www.random.org to roll your die 60 times, roll 60 dice all at once. So it's a very quick way to do it. Or you can pull a die out of a game that you have at home and roll it yourself 60 times. All right, so press pause, do that, and when you're ready, come back and fill in what your proportion or your p-hat is. All right, so for the video, I'm going to use my result. So my p-hat, which was the proportion of 60 rolls that resulted in a 6, I had 14 out of the 60 rolls end up as a 6, and so that's about 0.233. So you can keep in mind these are my results, or your instructor's results, and they may not match yours. All right, next up, calculate your test statistic. So keep in mind this is specific to your sample. So this test statistic compares the value of your p-hat with the value that the null hypothesis says we should see, which is p subscript 0, or p naught, in terms of standard units. So we're doing a z-score. Same idea as we did when we did z-scores earlier. We take our observed value, it's a value from our sample, compare it to the center of our distribution, and divide by the standard error of that distribution. All right, so for my results, I take 0.233 minus 0.17, divide by the standard error, and I'm going to use the more exact one, and that gives me a z-score of about 1.31. And I'm going to round the 2 digits here, just like we did before, because that's how our table is set up to accommodate. All right, next up, calculate the probability of getting a sample result this extreme or more extreme. So as big as I found or bigger. And what this is referred to is a p-value. So the p-value is going to be measuring our surprise. At our outcome, or p-hat. And this again is all if the null hypothesis is true. So if the die is fair, this is going to tell me how surprised I should be at my outcome. All right, so down below we're going to do 2 times the probability that I get a p-hat greater than 1.31. As extreme or more extreme than my sample proportion. So as big as 1.31 or bigger. Okay. Oh, and let me erase that just for a moment. I've got my notation mixed up. So I'm going to do 2 times the probability that I get a p-hat greater than 0.233. And that's the same as getting 2 times the probability that a z-score is greater than 1.31. So if you notice before I had z-score paired up with the p-hat, so I fixed that. All right, so I'll leave it up to you to double check the table for that the probability that goes with that z-score. So again, press pause, try this out. And hopefully you come back with an area of 0.0951. And when I double that, I'm going to end up with 0.1902. So here's my p-value. All right, so we don't know what a p-value is quite yet, and we have a slight definition up above, but let's look at it in more detail. So here, p-value is a probability, again assuming the null hypothesis is true, of obtaining a test statistic at least as extreme as the one actually observed. Extreme means in the direction of the alternative hypothesis. So remember, alternative hypothesis was that we just thought the die was unfair, that the proportion of 6s wouldn't be 1/6. All right, and this should be a colon there. Since our alternative hypothesis did not specify direction, we need to look at sample results that are as extreme as the one we found in both tails of the standard normal distribution. In other words, really big values of p-hat, a lot of 6s would support it, and very few 6s, a very small p-hat, would also support the alternative hypothesis. All right, and one last note here before I go on. What we want to keep in mind, this is important, is that small p-values, the smaller your p-value, are going to be rare if the null hypothesis is true. In other words, if your die is fair, it's very unlikely, it's going to be very rare that you get an extremely high proportion of 6s or an extremely low proportion of 6s. Okay, so next step, we're going to mark the location of our test statistic on the following standard normal distribution and shade in the area between our test statistic and the nearest tail. Then do the same for the other tail. So remember, our test statistic, our z-score was 1.31. So that's roughly, let's see, about there. So here's 1.31, and p-hats that are greater than that or more extreme would be above it. But we also want to mark negative 1.31. Remember, small proportions of 6s would also support the alternative hypothesis. So any p-hat down here would also be as extreme as the one we got, or more extreme. All right, so keep in mind that this area that we found from our table was 0.0951, or 9.51%. And because of the symmetry of this curve, or distribution, this area over on the left is also 0.0951, or 9.51%. And that is why we doubled that p-value earlier. And we needed both of these areas. So the total of these two areas is 2 times 9.51%, or 19.02%. And that total area is your p-value. Okay, so step 4, we got to interpret our result, and we have a choice between the two following decisions. Our first choice is to reject the null hypothesis, and this means we have evidence that suggests the die is not fair. In other words, that p is not 1/6. Right? The other choice is not to reject the null hypothesis. In other words, we don't have enough evidence to suggest the die is not fair. Keep in mind, we're not accepting the null hypothesis, so this is important. We're not rejecting it, but it doesn't mean we accept it. So we don't accept the null hypothesis. In other words, we fail to reject it. Okay. So keep in mind, we're not proving that the null hypothesis is true, which is why we want to stay away from the word accept. We're not proving that the null hypothesis is true, just that there is a lack of evidence to refute it. All right, so what should we conclude about our die? All right, well, in this case, I would say that we should not reject the null hypothesis. In other words, we don't have enough evidence to suggest the die is not fair. In other words, our proportion of 6s wasn't all that extreme, so it didn't really give us any evidence to suggest the die is not fair. So other thing to remember here, okay, it's the big piece. We are not proving either of these choices are true. So we're not proving anything. We're really just picking the choice that's more likely. So we're not proving the die is fair or unfair. Oops, die is unfair or fair. Again, we're just saying which hypothesis we have more evidence to support. Okay, these decisions are typically based on how small our p-value is. The smaller the p-value, the stronger our evidence is against the null hypothesis. And the smaller that p-value, the more extreme our result is if the null hypothesis is true. So how do we decide how small the p-value has to be in order to conclude that our die is not fair? Well, we do this by choosing a significance level alpha. So remember, this was mentioned back in step 2, and we normally would do it back there before we collect our data. We left it to the end right now just to get a better understanding of it. So in this case, if our p-value is less than our significance level, and this is the Greek letter alpha, then we reject the null hypothesis. And the most commonly used value is alpha equal to 0.05. All right, so alpha, I'm just going to make a note here. Alpha is really the probability that we make a mistake in rejecting HO, or the null hypothesis. So it's a probability that we mistakenly reject the null hypothesis, which is HL. Okay, and the other piece here, I just want to put this into symbols. So if our p-value is less than our significance level, so if your p-value is less than alpha, then we reject the null hypothesis. All right, so based on this more clearly defined way of coming to a conclusion, should we reject the null hypothesis? Is your p-value, if you're using mine, is our p-value less than alpha equal to 0.05? So if we reject the null hypothesis, then we're saying that our results are statistically significant. So remember, our p-value was equal to 0.1902, or 19.02%, and this is greater than alpha equal to 0.05. So this tells us not to reject the null hypothesis. So we should not reject the null hypothesis. Again, our result was not extreme enough to convince anybody that the die was not fair. Okay, so next piece, is it possible that we could reject the null hypothesis even though the die is fair? So that would be a mistake. What is the probability that we make this mistake? So it is definitely possible. The probability of doing that is actually 5%, and we call this a type 1 error. You don't really need to remember the name of it, but just know that there is a name out there if you're interested. In this case, the type 1 error is the probability that you reject the null hypothesis when the null hypothesis is true. And this is equal to alpha. All right, there's another type of mistake you can make. So the last bullet here, is it possible that we could fail to reject the null hypothesis even though the die is not fair? The answer is again yes, you can make that mistake too. And this is called a type 2 error. Okay, and using the notation from above, this is the probability that you fail to reject the null hypothesis, given that HO is false. There's a symbol for this probability. Beta is usually used, that's the Greek letter beta. But we're not going to be able to measure or calculate this with the information we've been provided. We would need to know the true value of P, the true population proportion. So again, we're not going to be able to calculate this given what we have. More advanced stats classes will go into that, but this class won't. It's just important to know that this type of mistake is possible.